Hey class. So today we would have been lecturing about the sine wave, which I previewed the other week, last week. But this week we would get into more details about that. So all of these notes, not only for the sine wave, but also for cosine, amplitude, and period, which are going to be the sections we'll cover this week. All those notes are on Schoology. Excuse me. All those notes are on Schoology, so you can download those if you'd like. But let's just jump into this lesson. So this is the first objective where we're going to just look at the graph and the properties of sine. So to first sketch one of these graphs, it's really good to look at these charts and tables that we know from the unit circle. So if you have your unit circle near you, it'd probably be good to take those out so that way you can see where these values are coming from. So let me just get the pin working. Cool. So if we look at table 1, okay, this isn't working, hold on. Okay, there we go. So table 1, its values are going to be, for 0, we have sine of x is 0, the y coordinate is 0. For pi over 2, I don't know why it's highlighting it, but for pi over 2, we have 1. For 3 pi over 2, we have, oh, I skipped one, sorry. -1 for pi, should go right here. We have 0 again, and for 2 pi, we have 0. So let me scroll down a bit and talk about this. So remember that our sine, when we look at our unit circle right here, if we have some point, like for 0 degrees, let's call it 0 degrees, even though it's not really straight, you had the coordinate 1, 0. And the x was our cosine value, and the y was our sine value. So all I'm doing right now is looking at the theta here on the unit circle and assigning that y value, that sine value of our coordinates to this function. So if we just sketch this 0, 1, 0, -1 on a x-axis, like so. So we'll do the y being the output and the x being the input. So the x is going to be some radian measured angle. Right. And the y is just going to be our y coordinate. So we have a 0 at 0 degrees at pi over 2. Let's call this pi over 2. We have 1. Call that 1. Okay. Word is so weird. Sorry, guys. So there we go. That's our point. And then at pi, we have another 0. So we have this. At 3 pi over 2, we have a -1. So that'll be down here. And then at 2 pi, we have another 0. That'd be right here. And if we were to try to graph just a sketch of this right now, connecting all these dots, it would look something like this. Okay, and this would be our first sketch of a sine graph. Excuse me again. And basically, if you excuse me again, I muted my mic. So basically, if you look at these tables and you take the y coordinate and fill each of these tables in, all of these values in, you'll be able to get a clearer picture of what the sine graph looks like. And basically it'll fit this this graph pretty well, right? So you'll have your pi over 3 here, pi over 4, and pi over 6, and those numbers will be kind of increasing to 1, right? But notice that the maximum that we hit is our 1 and our -1, right? And that's constrained by this unit circle over here. So, yeah, that's something to keep in mind on, and something we'll go over in the characteristics. But for now, let's move on to the next slide instead of filling out all of those tables, because this is what it looks like when you fill out all of these tables. So, this might be a little overwhelming as far as numbers go, but what you can see here is pi over 2 and 1. Here is pi 0. Here is 3 pi over 2 and -1. And here is 2 pi 0. So these were the points that are mapped out above, right? So then all these points are the first quadrant points. So that's Q1 on your unit circle. These 3 points right here are quadrant 2. These are quadrant 3 of our unit circle. And this is quadrant 4. So you've seen all these points before. Basically, the only thing that's happened is that we've reset. It's so annoying. So we've kind of like rolled out the unit circle onto a graph. That's kind of how I visualize it. I'm not sure if that helps you, but as you can see, again, like all we're doing is taking the measurements from the unit circle and saying, all right, well, what happens when we plug these measurements in to the sine function? And what happens is you get the y coordinate on the unit circle for your output. So for pi over 6, you get 1/2, and so on. So I just put some important notes here down at the bottom, right here. So our x-axis is measured in radians, not degrees. Our coordinate points are now theta, y. So all I mean by that is if you look at these coordinates, it's still xy, but our x is now some radian measured. So I wanted to kind of point that out. And if we extended the function in either direction, we would see the same shape repeat every 2 pi. So I would ask you to like kind of think about that for a second, maybe pause the video and ask yourself why it would repeat every 2 pi. Okay, so the reason why it repeats every 2 pi is, remember that if we have something like sine of, say, 7 pi over 2, we started evaluating this by finding the least non-negative coterminal angle for C, or sorry, for theta. And in the case of 7 pi over 2, we would have subtracted 2 pi from that, which would be the same as subtracting 4 pi over 3, or sorry, 4 pi over 2, which would wind up giving us 3 pi over 2. And so we could evaluate sine at 3 pi over 2, and this would be the same thing as evaluating sine at 7 pi over 2. So remember that 7 pi over 2 is equal to sine of 3 pi over 2, which is equal to -1. Now we could make a point on our xy axes for the sine graph, where the x coordinate is 7 pi over 2 and the y coordinate is -1. So if we look up again right here, we see that, so we have the point 3 pi over 2 and its output, its y coordinate is -1, and then an angle coterminal with it has the same output. And this will be the case for all of our angles forever, right? any coterminal angle will have the same output as its least non-negative coterminal angle. So this pattern will keep repeating every 2 pi, because every 2 pi you get a new coterminal angle to this original sine graph right here. So that's why it repeats in either direction. Okay, so let's talk about this repeating every 2 pi. So this is what's called a periodic function. So a function is periodic if you can add some positive number, p, such that f of x plus p is equal to f of x. And this is the same thing that I actually just did, right? When I did sine of 7 pi, 7 pi over 2, right? This is the same thing as sine of 3 pi over 2 plus 2 pi, right? 3 pi over 2 plus 2 pi, that's just 7 pi, right? These are coterminal angles. And we already talked about how these will give you the same exact output. So in terms of this language, right? So we have this left side being f of 3 pi over 2 plus 2 pi, and that gives you the same result as f of 3 pi over 2. So we added a positive number to this and got the same exact value for our function. So that means this function is periodic. And the period of a periodic function is the smallest number p for which f is periodic. And what this means is that, so we know another coterminal angle to 3 pi over 2 is negative pi over 2, right? So sine of negative pi over 2. So remember, this angle is negative. So if we look at where it goes in the xy plane, it goes in this direction like that. And this is, in fact, where 3 pi over 2 is. So it is coterminal with 3 pi over 2. And sine of negative pi over 2 is the same as sine of, what is it? 7 pi over 2 minus 4 pi. Okay, so sine negative pi over 2 plus 4 pi is equal to sine of 7 pi over 2. Okay, so since all these angles are coterminal, we would get the same exact answer for our function. We would still get -1 for sine. So my point in doing this is showing you that we can add a number that's bigger than 2 pi and still get kind of a period, right? The definition of a period. Because a function is periodic as long as we add a positive number p such that we get the same values for f of x and f of x plus p, right? So your period that you're trying to solve for is just going to be the smallest number that you can add. So if that's still unclear, I have another example on the next slide that we can go through. Right. So let's just go through this example and leave that one where it is. So we want to evaluate the following expressions. So if we look at A, right? All right, so what I'd actually ask you guys to do is pause this and just really quickly run through these examples and try to solve these expressions. Okay, so if you did that, you know that A, sine of pi is just 0. Sine of pi plus 2 pi is sine of 3 pi. And if we look at our xy plane, or you can just subtract 2 from it. Either way, you'll find that your angle looks something like this, which will still give you 0. And the same goes for sine of 5 pi in C. We get 0. So all three of these functions give you the same value. And what we did was take pi is equal to x, so x is equal to pi, in terms of our periodic definition, right? So that's our definition for something being periodic. We defined x as pi, and then we added a 2 pi and a 4 pi. And both of those satisfy this definition, so they both satisfy p. However, since 2 pi is less than 4 pi, that means that 2 pi is our period. So this is how you find the period of a function. Okay, so one note that I will say about this example is that there's actually another number that we could add right here for this specific example where x is x is pi. There's another number that I could have added that's not a multiple of 2 pi, and I would have gotten the same answer. However, if you see that, I want you to try and apply that same other number I could have added to a different example, for example, like sine of pi over 4, and try to add that and see what happens. But if you don't see that, if you don't know what I'm talking about, don't worry about it. It's just specifically when x is equal to pi that this happens, but it doesn't apply to other cases. Okay, let's go on to the properties of this sine function, because this is kind of where a lot of information is, right here. So let's talk about a few things. The domain of this function is negative infinity to infinity. So it might be a while since you've talked about domain and range, right? So the domain, D, is just what inputs you can put into this, right? So it's just talking about, well, what can I evaluate sine for, right? X can be literally a negative a billion pi or positive a billion pi. It doesn't matter, right? We can still find the sine of that rotation. However, the range, R, is the outputs, and this isn't infinite. So like I said in the first slide or second slide, the maximum of our sine function is positive 1, and the minimum is negative 1. We can't go outside that range. Again, we're constrained to our unit circle. This is only for the y equals sine x definition of it. So you'll see definitions in the next two objectives that change this maximum and minimum. But for now, when we're just dealing with y equals sine x, our maximum is 1 and our minimum is negative 1. And this is because of the unit circle. You can think of it like that. So the function is periodic with a period of p equals 2 pi. That's what we just went over. The y-intercept is 0, right? So it hits the y-axis on the 0 right there. And then the x-intercepts are of the form in pi. So this is something you're going to be seeing more frequently as we talk about sine and cosine. You'll see something like the zeros of a function being defined in terms of in pi or in over 2 pi, where n is an integer, something like that. So when you see something like that, think of the k from our coterminal angle family, right? So we did theta c equals theta plus 2 pi times k, or 360 times k, and k was just either a positive or a negative integer. So this is the same thing. So n is going to be an integer. That means that pi is going to be a 0, 2 pi is going to be a 0, 3 pi is going to be 0, and so on. Similarly, negative pi is a 0, negative 2 pi is a 0, and so on. So here I'm setting n equals 2. Here I'm setting n equals negative 1, and so on. This is n equals 3. Right. And you can look at the graph to see that. So we have a 0 at pi, we have a 0 at 2 pi, 0 at negative pi, and 0 at negative 2 pi. Okay. So the next thing is that this is an odd function. So odd functions are another big thing that maybe you haven't talked about before in a previous class. But an odd function says that if you have a negative input to your function, this is the same exact thing as a negative of the output of, I said this weird. So an odd function tells you that if you input a negative, that'll give you the same thing as if you input a positive and make the output negative. So if we look at, let's do an example. If we look at sine of negative pi over 3, or pi over 2, this is going to be equal to, remember this is equal to sine of 3 pi over 2. This is from the example earlier. I just added 2 pi to this, which is negative 1. Okay? So now let's use the odd property of sine to evaluate this differently. So we're going to keep the pi over 2, but we're going to make it a positive. So we're going to input a positive. So positive 2 pi over 2. Okay, now looking at our unit circle, we know that the sine of pi over 2 is a positive 1. So if we add a negative on the outside of this sign, that means that we're making the output of this function negative, and since it is a positive, we get negative 1. And if you look, these two are the same output. So this is what an odd function is. So if you put a negative input, you can just kind of distribute that negative out, take it out of the sine function, and evaluate that radian measure and its positive measure, and then make the output negative, which is all I've done here. So this is what's called an odd function. Okay. All right, so let's move on. It might help you if you know that the graph is symmetric about the origin. So what that means is if you go this way in the positive direction, then you go this way in the negative direction. So you see how that's kind of symmetric like that. So you can kind of flip it back and forth to go positive or negative. Okay. So the relative maximum and relative minimum are here and here. So basically this is just saying anything coterminal with pi over 2 is going to give you your maximum. Anything coterminal with 3 pi over 2 is going to give you your minimum. So notice that this is 2 pi n, which is just, it's the same thing as saying 2 pi k, right, in our coterminal formula. So you can just look at these relative minimums and relative maximums as saying these are the angles, you know, your x has to be coterminal with in order to give us a minimum or a maximum. So again, you can kind of get that information from the unit circle, right? So we can do some examples, right? So we can list all of the values of the x interval on the interval negative 3 pi to 7 pi over 2 that satisfy the ordered pair x, 0. So this is saying list all the values that give you an x, a 0, right? A 0 for the sine function. So let's look at our zeros definition. up here. So remember, our zeros are of the form in pi, where in is an integer. So that's this stuff right here, right? In pi, zeros. Okay, so let's look at our range again. So -3 to 7 pi over 2. So remember that this bracket means that it's included, right? So that means that this -3 pi is included in this range. So that means our zeros are going to include -3 pi. Okay, now I want you to pause the video if you haven't already and try to figure these out for yourselves. Okay, so let's look at the second, the maximum, 7 pi over 2. This is less than 8 pi over 2, right? Which is equal to 4 pi. Right, because 8 divided by 2 is 4. So that tells us that we don't really get to 4 pi. Okay. So the maximum that we can get is 3 pi. All right, so we get -3 pi, -2 pi, -pi, 0, pi, 2 pi, and 3 pi. Now that I'm looking at this, I feel like there's more answers when I do this now than there should be, so give me a second. Okay, so I must have had a typo in my notes when I wrote down the answers to this, because I just kind of drew 7 pi over 2, this angle right here. I drew it so that way I could check that we cover all of these, and we do cover all of these right here. So even though my notes, if you scroll down, you'll see the answers. Even though my notes stop at pi, it should actually include 2 pi and 3 pi. Not sure why I didn't. I'll have to check on that later, but yeah. So those are the answers. So they're all the in pi solutions that give you a 0 as your output. Okay, so we just have 2 more examples. So here we have the periodic function, or periodic property, and we want to use that in order to solve y equals sine x. So we want to see what's equivalent to sine of 23 pi over 6. So using the periodic function is going to be the same thing as finding the coterminal angles, right? Because they are the same. 2 pi is the period, and 2 pi is also what you use to find the coterminal angles. So let's do that now. 23 pi minus 2 pi, because we're trying to find the least non-negative, so we're doing a minus 2 pi. Well, that's going to equal, again, we can put that in our calculator as 23, use the ABC button to make it a fraction, and then subtract 2. All we're doing is ignoring the pi for now. So when we do that, we do 23 over 6 minus 12 over 6, which is equal to 11 over 6. We can add the pi back, and 11 pi over 6 is our coterminal angle. So looking at our possible solutions, we see 11 pi over 6 right here. So that means that C is going to be our, sorry about that. That means that C is going to be our solution. So let me get back to where I was. Here we were. Okay. So C is going to be our solution right here. Okay. And the next slide is just saying that C is in fact our solution. And then we have our last example. So use the fact that y equals sine x is an odd function to determine which of the following expressions is equivalent to negative sine 9 pi over 16. So remember that sine of negative x, because it's an odd function, is also equivalent to negative sine of x. Okay, don't know what happened there. Sine of negative x is equal to negative sine of x. So all we're doing here is asking kind of the reverse, right? So we have the negative sine of x here. So all we have to do is put the negative inside of the parentheses, and that will be equivalent. So if we scan our solutions, we see that A is the solution that does that. So A is going to be equivalent. And in fact, we see that. So that is all for my notes on this section. I can upload these filled out notes to Schoology as well. But for now, that's it. I know this video was long, but I kind of wanted to make it long because it's hard to fill all of this information in a 5-minute video. So I hope this helps, guys. I'll see y'all tomorrow. Yeah, and have a good one.